So, good morning, everyone. Hope you have pleasant stay. So, welcome to the CMRT. And so today the first lecture is by Professor Balasubramanian. So, I welcome Keshav to introduce him.
Thank you, Saurabh. So it is my pleasure and honor to introduce Professor Balasubramanian. He does not need any introduction, really. He's an extremely distinguished and a senior mathematician, and his work on the variance problem and circle method is extremely well known. And people have still been, exploring all of these techniques and finding new methods and new results. So without further ado, Professor Balu, please.
Thank you. Let me first of all express my thanks to Saurabh Singh for this opportunity to be able to talk on something on circle method, particularly variance problem and Goldberg's conjecture. One can probably say that the origin of circle method is contained in a letter written on 16th January 1913 by an unknown Indian clerk from the Port Trust to Hardy, where he writes what are the type of problems he is interested, and one such problem is the coefficient is of x power n in 1 minus 2x plus 2x power 4 minus 2x power 9 plus 2x power 16 minus etc. inverse is the integer nearest to 1 over 4 pi cosine hyperbolic pi root n minus sine hyperbolic pi root n by pi root n.
Sir, can you write a little bit bigger?
Okay. Oh, I see. Okay. Let me see whether I have written it correctly. Yes. Yes. And Hardy's first remark after seeing this formula is this is quite untrue. Okay, and probably I will explain in what sense it is quite untrue. And but then he says, but the formula is extremely interesting for a variety of reasons. I mean, how could that be a formula which is not true but still an interesting formula for quite a variety of reasons? The point is that this is the main term in the approximation. Therefore, the main term is exactly correct. Okay, what is wrong is that Ramanujan seemed to have felt that the error term is O of 1, nearest integer, and that definitely is not true. The error term is much bigger, but the main term is perfect. Okay? And then Hardy and Ramanujan used this idea to prove something on partition functions, which I am not going to talk about. And then Hardy and Littlewood realized that this problem can be also used to solve Waring's problem, Goldbach's conjecture, etc. And then this method underwent a good improvisation by many people, starting with Hardy and Littlewood and Vinogradov, Harold Davenport, and recently Heath Brown, Woolley, Vaughan, Deshouet, and others. Okay, and therefore I am not going to start from the history and say how it has transformed. Therefore, now let's take more or less how the formula is around 1980s and 90s. Okay, and this was not the original one. I mean, it has really undergone a lot of changes. And therefore, I should probably talk about what is this Waring's problem. Let K be a natural number. First question, prove there exists another natural number S depending only upon K such that every integer n can be written as sum of S kth powers. But that's where we start, that you want every integer to be the sum of S kth powers. And once you settle this question, the natural question is, if so, what is the smallest S? That should be the obvious next question to ask. And this particular number is denoted by little g of k. And this also gives rise to a third question. First of all, I have to introduce the third question. Suppose k is equal to 3. And then you want to write every number as a sum of cubes. And then you want to know how many cubes are needed. Okay? And what would be the guess whether a small number like 23 will need more cubes or a big number like 1048,718, this will need lot of cubes. Okay, this is the thing. And then you can try to do some computer simulation, and that would show that actually the small number needs a lot of cubes than the big number. The reason why the small number needs a lot of cubes compared to the big number is that less than this 23, you have only 2 cubes to play with, 1 cube and 2 cube. Therefore, if you want to write the 23, you have to somehow manage only with 1 cube and 2 cube. Whereas if you have a big number, then you have a lot of cubes to play with. You can play with, oh, sorry, I should have been made very clear. Xi greater than or equal to 0. Some of the zeros are all allowed. Then you see, you have all the way from 1 cube to 2 cubed, etc., up to 1000 cubed. No, probably 100 cube. Therefore, too many cubes are there for you to manage, play with. And therefore, you can manage it. And it so happens that that is in fact true. For example, the 23 needs nine cubes, because you have to only manage with 1 8 and another 8 and 7 ones. You can't do anything better. Okay? And it is in fact known that 23 and 239 are the only numbers which you need 9. All the other numbers you need only 8 at most. Because once you have a bigger number, then there are a lot of ways you can play with. Okay? And therefore, what happens in the very small numbers is not that interesting. Because that is essentially forced by the fact that you do not have too many cubes to play with. What happens for big numbers is what is more important. And that takes the question number C. The smallest S, for which every large n is a sum of s kth powers. Okay, and this number is called capital G. Okay. Okay, we will do the A, but the B is almost solved, and therefore we won't bother about that. That is essentially because for small numbers is the one which is going to count, and the small numbers you can manipulate. Okay, because they will need the largest things, and therefore if you know how many are needed for small numbers, then you are essentially happy. And the C is practically nothing is known. Therefore, the question remains really wide open. And in fact, capital G of 2 is equal to 4 was proved by Lagrange. And capital G of 4 equal to 16 was proved by Davenport and L dash sort of independently. And essentially that's all. Okay? We do not have a value of the G of K for any other value of K. Good. Then the other question is called Goldbach, which again most of you would have known. And this has a binary problem. If n is even, bigger than or equal to 6, then this n can be written as sum of two prime numbers and a ternary. If n is odd, then n can be written as sum of 3 prime numbers. And again, B is known due to Herald Helfgott, but the proof runs to more than 200 pages. I mean, the calculations are terrific. Okay, and therefore it is also not a bad idea to know what are the ideas of the proof, so that one can probably try to see what is that one can do that. And now I start, therefore now we sorry? Huh? Oh, that's the difference which I was saying. Okay, for example, you want to write every n as a sum of s kth powers. Okay? As we will see a little later, the larger the s, it is easier to prove, because when you have too many kth powers, you can easily write. The smaller the s, you cannot prove. Okay? Therefore, if you have a large s, it is easy to prove, but small s is difficult. Now, what happens is that if you want every n to be represented, the small n's need a lot of s. Since the small n needs a lot of s, for that s only you have to prove the result, which turns out to be somewhat easy. Okay? Whereas, if you want to know what is the minimum s for which every sufficiently large number can be written, the corresponding s is small. Therefore, you are forced to prove for the small s. Okay? For example, as I told you, for cubes the result is not known. Okay, for fourth powers the result is known, we can really talk. Fourth powers, the answer for the question B is 19, and the question C is 16. Okay? Therefore, if you want to write every number as sum of fourth powers, you need 19 of them, because for example 79 needs 19 fourth powers. Again, for the same reason that you can manage with 1 power 4, 2 power 4, and that's all. 3 power 4 even you cannot deal with. 3 power 4 is 81. Therefore, you have to manage with 1 power 4 and 2 power 4. Whereas 16, whereas large numbers need only 16, as Davenport has proved. And therefore, for s equal to 16, you have to prove this. And as you can clearly see that proving any such result for s equal to 19 is fairly easier compared to the proving the result for s equal to 16. And for cubes, of course, 9 is needed, as I was telling you, for the first B question. For the C, we do not know the thing, but more or less we believe 4 should be sufficient. Okay? Good. And this is something which I will talk about a little later, because then there is something called local solutions, and what is the s that is needed to get the local solutions for every Archimedean and non-Archimedean primes, and more or less we guess the maximum of that should be probably the correct number. Therefore, now that's the theorem you want to prove. That okay, therefore I'll prove start with a somewhat a very weak theorem and then see the ideas behind it, and then these ideas, then we have to see how to tighten the S. For example, let us take S is equal to something like a 2 power k plus 10, some number. Then I want to prove that every n can be written as sum of s kth powers. Okay. However, when you even start for this question, you want to write the n as a sum of kth powers. Okay, as I told you that I am going to talk about how people do it around after the 80s, etc. Earlier there was, therefore you will find some words like arc, etc., whereas there will be no circle for everything. And in the circle method which we are going to discuss, there will be no circle anyway. Okay, it started with the circle, and then under the various transformation, the circle disappeared. Okay, you will do the following. Let's define my capital N to be n power 1 over k, the integral part of that. And then you take the function f of alpha is equal to summation e power 2 pi I alpha m power k, x power k with 1 less than or equal to x less than or equal to n. Okay, and in most of the books on circle method, you will see this as written as this. It is a little boring to write every time e power 2 pi, particularly when you want to type and things like that. Having one thing above the thing, etc., is all difficult. Therefore, this is a shorthand notation that is used. E of x always stands for e power 2 pi x. And then raise this to the sth power. When I write this is to the sth power, what I am going to do? I am going to write the f alpha again and again, that's all. I write f alpha s times. Okay? And then I multiply. Once I multiply, I get summation x1, x2, etc., xk, xs, e of alpha into x1 power s plus x2 power s, sorry, x1 power k plus x2 power k plus etc., xs power k. And with all the conditions that all the xi's are less than or equal to n. Okay, and now when you do that, the different tuples x1, x2, etc. xs can give you the same x1 power k plus x2 power k plus etc. xs power k. The same number can occur for different values of these, and therefore this can be always simplified as summation over m r of m e of alpha m, where r of m is the number of ways of writing m as x1 power k plus x2 power k plus etc. xs power k, which is an extra condition that xs is less than or is equal to n. xi is less than or equal to n. That is, since a different s tuples x1, x2, etc. xs may give the same value of m. Therefore, see what is the coefficient of e power 2 pi I alpha m. The coefficient of e power 2 pi I alpha m would be the number of ways that m would come, which is the number x1 power k plus x2 power k plus xs power k. And which this number I call r of m. Therefore, what is that I have? I started with an f alpha power s, and I wrote the Fourier expansion for it. And we all know that when you write the Fourier expansion, how to get the Fourier coefficient. This is the integration. Therefore, R of m is equal to 0 to 1 f alpha power s E of minus m alpha d alpha. Whereas, which is what I have written, R of m is the number of solutions of that equation. In particular, let's put m equal to n. Whereas R of n is equal to x1 power k, the n can be written as x1 power k plus x2 power k plus etc. xs power k with an extra condition that xi is less than or equal to p. Okay, that's all what it is. Therefore, R of n is the number of representation of n as sum of kth powers where the summands are all less than or equal to p. Okay. Now let me say something. Suppose you are able to write n as the sum of s kth powers with the xi bigger than or equal to 0, then such an xi power k is naturally less than or equal to n. If you write n as x1 power k plus x2 power k, the xi, every xi is bigger than or equal to 0, then every xi power k has to be naturally less than or equal to n, which is the same as saying that this xi naturally has to be less than or equal to capital. Oh, xi is naturally less than or equal to capital N, because the capital N is by definition n power 1 over k. Therefore, putting this condition that xi is less than or equal to capital N is no condition at all. When you try to write n as an x1 power k plus x2 power k plus xs power k, this xi will all be naturally less than or equal to n. Therefore, this condition can be omitted. Sorry? Yeah. Oh, 0 included, of course 0 included. Of course, unless you include 0, of course. Yeah, because I am only looking at xi bigger than or equal to 0 type. But anyway, even if I don't include 0, it doesn't really matter, because at that level there will be a lot of solutions. Therefore, not only xi equal to 0, even if I omit, there will be a lot of solutions. Anyway, therefore now I can reinterpret my question A, that can you prove that for m, yes, some, yes, every n can be written as x1 power k plus x2 power k plus xs power k is equivalent to, therefore my question A is equivalent to prove Rn is positive. Rn is a number of ways of writing n as x1 power k plus x2 power k plus xs power k, and then you want to prove that if the n can be written as x1 power k plus xs power k, then you have to prove that there is at least one representation. Therefore, what we have done essentially is we wanted to write n as sum of kth powers, we were wondering, and finally we reduced it to evaluating a certain integral and proving that that integral is positive. Is that okay? And therefore, our whole thing would be essentially how to prove the integral is positive. And then any other classical use of circle method, like what he is going to talk about, when he is going to talk about, again it will be the same. You will finally reduce everything to the integral due to. Good. Therefore, that's the question. That's what we are going to do now. Therefore, now our aim is defined. Therefore, you have this integral and we essentially aim to prove. Therefore, how to do this integration? Good? Good. Therefore, now let's start with the first step, where I will prove nothing at all, everything would be hand waving. From the earlier analogous questions which you were raised, like for example, partition function questions and some computer simulation, seems to show that the graph of mod f alpha looks like between 0 and 1 something like that, which means uniformly small peaks at A by Q big peaks for small q. That is how the graph looks like. Okay, normally very small, but when you have a look at a rational number A over Q, and in A over Q, and that there it has a peak, and even that peak is a big peak only when Q is small, and it is a small peak even if Q is large. And therefore the large Qs won't matter, only small Qs. Okay. Once you have an idea at all how the graph of phi alpha will look like, we have some idea of how to proceed the problem. Namely, break the integral into two parts. The one part is neighborhood of because this is where you expect the contribution to come from, since you know the contribution essentially comes only from the peaks, which are the peaks are neighborhoods of A over Q with the A and the Q being small. Therefore, this is probably what it should be the main thing, and then hopefully that this contribution should be small. And that's exactly what we are trying to prove. We will break this into two parts and we will prove that contribution is small and this contribution is big. Okay? And this funny thing is called the major arc. Which one gives a major contribution, and it is called a minor arc. Okay? Okay, now therefore we go to the second step, which is still hand waving, but a little detail. Yes? Sorry? Oh, that is some P. I mean, because I know that P I am going to now define, but therefore this is how it will look like. Okay? Therefore, since a major contribution comes from the arcs around A over neighborhood of A over Q for small values of Q, which is what more or less the analogy from the earlier theorems as well as computer simulation shows. Therefore, this is what we are trying to do. Is it okay? Okay, now that you wanted, let's define all those things now. Before I goof. Okay, therefore the notation is n is equal to n power 1 over k as we have defined. And let us define p to be n over 2k. And mqa is a neighborhood of a over q, which is a over q minus p over q times n, a over q plus p over q times n. And the major arc is the union of such mqa, union over all a equal to q, aq co-prime, union over all q less than or equal to p. For the p which we have just defined. And the rest of them will be minor arc. Is it okay? And now what do we do? Okay, therefore now, okay, first of all, anyway, okay, we'll come to that, okay. Anyway, how many solutions would we expect? Let's look at that question. What would be the order of the integral? Because, you know, you have to look at the main contribution, the small contribution, and you would like to know which are the small contributions that can be omitted. Therefore, the main contributions. And therefore, what is the number that you would expect? Okay. Therefore, you have your x1 power k plus x2 power k plus etc. xs power k equal to n. And you can essentially choose the first s of them any way you want, which is gives you every xi being less than or equal to n. And that would give you n power s minus 1. But then the last one has to be a kth power. The probability of kth power is only 1 over k, etc. And therefore, when you use all those things, okay, this is an exercise, that the expected number is something like an n power s minus k, which is the same as n power s over k minus 1. Therefore, this gives you an idea of what are the elements which you should keep, what are the terms which you should keep, what are the terms which you should omit. Anything which is smaller than n power s over k minus 1, you can omit. Okay. Now, how do we proceed? First of all, let's do this integration over mqa of f alpha power s e of minus n alpha d alpha. That's what we have. This integral is nothing but a over q. Before that, normally one makes a small things, and let me do that. Therefore, your major arcs should be like that. Okay, around any a over q, it will be of the distance p over qn both sides. Okay, that's how your major arc will look like. And now this is an exercise. The major arcs are disjoint. And in fact, their measure is small. Therefore, actually the main contribution comes from a set whose measure is small, essentially because that is a set where the integrand is very high. Okay. The set where the measure is big, the integrand is very small. And therefore, that does not contribute. Okay. And it is a small set, and therefore it is actually completely disjoint. And now what happens is, take the point 0, and the 0 can be written as 0 minus 0 over q, and if that number is less than 1 p over qn, that will be in the major arc. But since your interval is 0 to 1, therefore this part will not come, only this part will come. Only one part. Therefore that is one single interval which will have a length q over n. Every other interval will have a length 2p over n. Correct? Because in the left hand side you have p over n, the right hand side p over n, therefore it will be 2p over n. Whereas the intervals around 0 alone, as well as the interval around p and around 1, because 1 also has an approximation here as 1 minus 1 over q over q. And the 1 also has an approximation 1 over q, and therefore around p over n, that will be there. Okay, but that there are only two intervals, the extreme intervals, which are of the length p over n. Every other interval is of length 2p over n. Okay, and that is a little boring, because every time then you have to remember that there is a one interval of p over n, etc. Therefore, instead of that, instead of 0 to 1, now if you take this interval, as far as the Fourier inversion is concerned, it doesn't really matter. You can take any interval of length 1, and therefore you don't have this 0, but you have 1, but then this 1 will have both this side as well as that side. Therefore, every interval will be of the length 2p over n. Okay? Therefore, instead of 0 to 1, if you take p over n to 1 plus 1 over p over n, I mean that then all these degenerate cases need not be discussed. Okay, which is normally done, but anyway that won't affect. I will continue with the 0 over n, but you always remember when I write 0 to 1, it is always means p over n to 1 plus 1 over p over n. Up to this, is it okay? Because now only the game starts. So far we have not really done much. Okay? Is it clear? Yeah. Okay. Now you look at this interval a over q minus p over qn to a over q plus p over qn f alpha power s e of minus n alpha d alpha, which you can now make a change of variable, minus p over qn to p over qn, f of alpha a over q plus beta power s e of minus n into a over q plus beta d beta. Now let me give you the first proposition, which will, these are the proportions which will prove f of a over q can be approximated by SAQ by q times n, where SAQ is equal to summation E of a by q m power k 1 less than or equal to m less than or equal to q. That was exactly the original problem we had in doing the integration. In doing the integration, the integrand, okay, changes rapidly. The integrand fluctuates widely. Since the integrand fluctuates widely, we don't even know how to handle it. But on the other hand, when you now take small pieces, okay, in each piece, the integrand behaves reasonably well. Since in every piece the integrand behaves reasonably well, you can actually do the integration. Okay, which is something, therefore this f of alpha cannot be approximated by a nice function throughout the interval. It's completely vanishing. For example, as you can see that this f of a by q depends upon the a and q very much. Okay, therefore for a different a by q, the f of a by q will be a completely different function. Therefore, since this function is widely fluctuating, we do not know how to integrate. But fortunately, since the main contribution comes from the rational points, and around the rational points we can actually integrate, do the approximation for the integrand, we can actually do the integration. That's the important point. And once you have this, then you can actually have an approximation even over a small neighborhood. Which we will define a little later. Which essentially means in this I can actually approximate f of a by q plus beta by known functions. Since I can approximate f of a by q plus beta by known function, I can actually do the integration. Okay? And therefore this gives you minus p by qn to p by qn, v beta etc. we will define on the way, and then you have an SAQ by q, v beta power s, e of minus n into a by q, e of minus n beta d beta. Is it okay? The next proposition. V beta is essentially supported around 0. Therefore, around 0 it will have a large contribution, and once you move away, little away from 0, it will have practically no contribution. Since, okay, therefore this is around 0, because you see p is only about n power 1 over k and q is also less than p, which is around n power 1 over k, and p over q is around 0, and that is where this contribution will come. Around this interval, of course, there will be no contribution, and therefore one can now write this as minus half to plus half SAQ by q, v beta power s, e of minus NA by q, e minus n beta d beta. Because essentially v beta is concentrated only around 0, therefore if you have an interval around small 0, you have this interval, then of course you can extend it to minus half to plus half, making it now completely independent of A and Q. Therefore the range of integration now has become independent of A and Q. And now we continue. Therefore, this is the contribution from one single piece of the major arc. Once you have a contribution from one single piece of the major arc, of course, I can now do the contribution over the full major arc. Therefore, the integration over the full major arc is equal to summation Q less than or equal to P, summation A equal to 1 to Q, AQ equal to 1, and then you have an SAQ by Q power S e power minus AN by Q and then you have this integral which can even come outside the summation because I have made it independent, minus half to half V beta power S E of minus N beta D beta. The advantage of making it minus half to plus half is essentially I can take it outside the summation. Otherwise, the range of summation, the range of integration was depending upon A and Q. And once it was depending upon A and Q, I didn't know what to do. But I can now do that. And now this is called Jn, which is called singular integral. And again I am going to do the same thing, namely that this series is fantastically convergent and therefore the summation up to P is the same as summation up to infinity, because for any very rapidly convergent series the first sum is already the full sum, and therefore this is summation Q is equal to 1 to infinity A of Q, where A of Q equal to summation A is equal to 1 to Q, SAQ by Q power S E of minus AN by Q. And this is called the singular sum, which is written with a curly S in the typed version, and I can't do a curly S in the blackboard. Okay. Therefore, now you see somehow we have at least done the integration of the major arc. The integration of the major arc has been now done, and it is now a singular integral times a singular sum. Okay. Therefore, it's not too complicated, and that's not again too difficult essentially because in every piece of the major arc I know how to approximate my function. Since I can approximate the function in every piece, I can just do the integration. Is it okay? And now the proposition. The singular integral is bigger than or equal to constant times n power s by k minus 1, which is what you would expect. You see, in this case, now there is no variance problem or anything like that. You have any V beta which can be given explicitly, and then you are just integrating it. And now, of course, about the Gn. The proposition Gn is bigger than or equal to a constant, And that is not exactly true, provided yes.
EQ does not have co-primality condition.
Which one? Oh yeah, AQ equal to 1. Oh, of course it has a co-primality condition. I mean, the same thing is what I have written. Okay, provided, and this is exactly what I was talking about the local. Provided this equation oh God, I need a new name. You see, if you really want a solution, then obviously locally it should be solvable. Unless it is locally solvable, you cannot solve it. Okay? And that should get reflected somewhere. And in our bearings problem, Goldberg sketch, in all such problem, that is reflected in the exactly in the singular sum. For any lambda, I mean integer. I mean, I wanted to put M or Q or something like that, but on the other hand, M, Q, everything I have used already in some different context, and I don't want a confusion.
X of S, not X of N.
X of S, yes. Okay. So that's what you would always expect, you know, that if you have a solution, if you want really a solution, then you should be having a local solution, and that would get reflected in the singular sum. And that will be much more clear when we do the Goldbach. Okay? Because what would happen in the Goldbach is essentially that if you are looking at the binary Goldbach, the singular sum will vanish if n is odd. Therefore, only at n equal to even you can expect it. And similarly, if you are looking at the ternary Goldbach, the singular sum will vanish when n is odd, n is even. Therefore, you can expect it only. I mean, that is where the fact that you need an odd or even would come, not in the singular integral. Singular integral will be high, always, the expected number. The singular integral will always gives you the expected number of solutions. But whether it has a local solution or not would be determined by the singular sum. And therefore, consequently, we have proved that the major R contribution is exactly what we expect, at least as big as n power s over k minus 1. Okay? Now, next proposition, this is a minor arc proposition. This is a thing by Hermann Weyl. You recall f of alpha equal to E of alpha n power k n does not equal to n. And the trivial estimate is n, correct? Because every term is 1, and then you want to improve a little. And the proportion of Weyl is that on the minor arc, mod f of alpha is less than or equal to n power 1 minus 1 over 2 power k minus 1 plus epsilon. You can save a little on the minor arc. And in fact, this is for the supnom. The proportion Hua, but if not the supnom, if you are interested in n power 2 power j is what you should expect, minus j minus 1 plus epsilon. Trivial estimate would be n, and you can say essentially j minus 1. I hope I have written it rightly. Weyer's inequality. Yes. And this is 2 power j. Yes. 2 power j minus j. Oh, wait 1 minute. Sorry. 2 power j minus j. That's all. That's no minus. 2 power j minus j plus epsilon. Yeah. Okay. And now we can more or less now complete the proof. We can complete the proof because we know the major R contribution. The major R contribution was n power s over k minus 1, which of course if you want you can write as capital N power s minus k. Correct? And now we have to prove somehow that the minor R contribution is a little smaller than that. I got to prove that the minor R contribution is little smaller than n power s minus k. That's all what I need. Therefore, now let's do the minor R contribution. What do we get? The minor R contribution of mod f of alpha over s d alpha. In the minor R, of course, I am not going to use any cancellation. I don't know anything about the function, and therefore I can't use my e power minus n alpha, anything like that. Since I don't know anything about the function except that it is small, and therefore I am not able to use this e power minus n alpha, the fluctuation, I am just going to do this. And remember, I am choosing my s to be something like a little bigger than 2 power k, something like that. And therefore, I can take s minus k outside, for the power s minus 2k, I take the subnorm outside, and then I keep the 2 power s, the rest inside. Then by Hua, this practically saves a 2 power k. Not exactly, but of course practically. Sorry. Yes? I'm not, yeah. No, I am using Hua's lemma. I am using Hua. You see, the point is, Weyer's lemma gives you a L infinity estimates and somewhat a weak L infinity estimates. Hua's lemma gives you LP estimates, somewhat recently strong LP estimates. Okay? And therefore, what I do is I take the s minus 2k outside, I keep the 2k inside, and then I use the LP estimate here, and then use the L infinity estimate here. Is it clear? Huh? You know, I mean, what I meant is the Hua's lemma will not follow from Weyl. Okay, Weyl gives you L infinity. Hua doesn't give you L infinity. Weyl gives you L infinity, but the L infinity is weak. Hua gives only LP. And the LP is reasonably strong LP. Therefore, neither of them is a consequence of other. Okay? You have a weak L infinity estimate and a somewhat strong LP estimate. And then you are trying to combine both to gain the maximum out of that. Okay? And this LP estimate by Huas, you can take only power 2 power k. When you raise to the power 2 power k, you can gain essentially a k. Up to an epsilon, when you raise 2 power k, you can essentially gain k. Okay? And the Huas method will not allow you to gain more than that even if you take a higher power. And therefore, you take only the 2 power k. And then you gain a k. Is it okay? Therefore, I essentially gained a k. Correct? And what do I need? I need essentially, over the trivial estimate, I need essentially to save a k and a little more. The trivial estimate is n power s, and I have to save a k and a little more. And what I have done is essentially saved a k, probably a little less. And that little less and that little less can be essentially covered by this. Here I have a saving of 1 over 2 power k minus 1 over the trivial estimate, and that should do. Is it okay? I think this is a little tricky part. Therefore, let me again say that the trivial estimate is n power s, because you are only integrating 0 to 1 f alpha power s e of minus n alpha d alpha, and f alpha is equal to summation n not exceeding n e of alpha n power k. And therefore, the trivial estimate is n. Therefore, here the trivial estimate is n power s. Okay? But in the major arc, you need the lower bound, and therefore, you cannot put the absolute value. Okay? Therefore, you have to live with the cancellation which would come from the exponential factor. And in the major arc, if you decide to live with the cancellation comes from the exponential factor, you lose exactly k over the trivial estimate. And this k is what you have to gain. Okay? And this k is gained essentially by Weyls estimate and Huas estimate. Huas estimate takes that if you are taking the L 2 power k norm, you can gain a k probably a little less. Weyls estimate says in the sup norm you can save 1 over 2 power k minus 1. And therefore you gain a k a little less in the Huas norm, and then whatever needed is gained from there. You can simplify this if you want. Therefore, our assumption that S is bigger than 2 power k plus 10 means that here already you gain a 2 and a little more, and that little more will kill that epsilon. Up to that, is it okay? And then we will try to now prove all the various propositions. Okay, we assume, but Practically, what is that we have done? Practically, what we have done is that you take the major arc, which is small pieces around A over Q, and in every major arc you can approximate your function by a nice function, okay, which may not apply uniformly to all the major arc, but major arc piece by piece you can approximate, and therefore you can integrate, and then after the integral everything follows, and the fact that that number is bigger than c into n power s over k minus 1 follows almost immediately without much trouble, as we will see. Therefore that part is over. Now we take the minor arc. The minor arc you do this. Is it okay? And now, again, whatever I was telling about the little gk is namely that practically it is known, and therefore I won't touch upon much, is practically true in this case also, namely the major arc part is essentially well understood. And we know everything that is to be known essentially on the major arc. Okay? And the minor arc is the one where we have absolutely no idea how to proceed. Okay? And therefore, consequently, therefore, I will just touch upon the major arc and go on the minor arc a little more carefully. Is it okay? Therefore, let me start with the Weyls theorem, Weyls lemma and Hua's lemma. Yes? Okay, now Weyls lemma. Therefore, let me prove this Weyls lemma now. Okay, even before starting Weyls lemma, there are two things which of course I will need for the Weyls lemma to do, and therefore let me do that. There is a, first of all, remember, the major arc was defined as there was the definition of the major arc. Okay, and we defined the minor arc to be the rest. Okay, such a definition is somewhat useless for us, because once you want to deal some with the minor arc and prove something on minor arc, I mean, such a negative definition is no use. You can't do anything with the negative definition. Therefore, you have to define the minor arc somewhat in a positive definition, so that I can do something with the positive. Is it okay? Therefore, let's give a positive definition for the minor arc. So that what do we know? Probably most of you would have seen this proof, the lemma due to directly, which is probably the first time he proved pigeonhole principles, namely, given any alpha, alpha minus a over q is less than or equal to 1 over qq has a solution. In q less than or equal to q. I assume that I can take this result for granted, no? Practically everybody would have seen this result. It's okay? And now take your q to be 1 over q, okay, n over p. If you take n over p, then it follows that alpha minus a over q is less than or is equal to 1 over p over qn for some q which is less than or equal to n over p. Therefore, any alpha has an approximation as a over q with such that alpha minus a over q is less than or equal to p over qn with q less than or equal to n over p. Is it okay? And then I'm going to define the major arc and the minor arc. It can have more than one solution. If any solution satisfies Q less than or equal to P, put this alpha in the major arc, otherwise put this alpha in the minor arc. Therefore, I am now treating both major arc and minor arc in equal footing. I am not saying the role is different. You write alpha minus P over Q equal to P over Qn, and if this, yes. Sorry? Yeah, even one will do. That's true. But anyway, 2 power k itself is already too big. And therefore, there's really no point. No, 2 power k, I mean, the point is that even 2 power k we don't expect. We expect O of k. And therefore, once you have O of k and therefore you have only prove a weak result O of 2 power k, then you will make life easier by taking 2 power k plus 10 rather than 2 power k plus 1 and then try to fight for it.
Why you take 10?
Something like that, anything. No, okay, the point is that this method will work only when S is bigger than 2 power k. If S is less than 2 power k, it won't work simply because I need to save a k from Hua's method and then I need to save a little more by Wales method. Since therefore I need a power 2 power k and also a little more. Even 2 power k plus 1 will do. Then you have to argue carefully, that's all. Okay? Therefore, if you decide to use Hua's lemma, then 2 power k is a must. There's nothing which you can do. Okay? But what we expect is more or less O of k. E of k. And therefore, we have a wrong way to go. And probably in the next lecture, I will try to give the Davenport's idea how to prove O of k log k. Okay? And in the O of k log a, improving the constant is a very, very difficult job. Okay, we'll come to that later. Okay? And first of all, are you convinced that this definition is the same as the original definition? Okay? In the original definition, I said that you take all A over Q and you take an intervals of length P over Qn, both sides of that, and take those alphas. Now I am saying you take the alpha, you take the rational approximation A over Q and then alpha minus A over Q, and if this any of the Q happens to be less than P, then you put the alpha in the major arc, otherwise you put it in the minor arc. Okay? Therefore, now I have given a positive definition for minor arc, which means the minor arc admits a approximation A over Q such that alpha minus A over Q is less than P over Qn, and that Q is bigger than or equal to P. Is it clear? Good. That is one thing which I need to prove the Wales inequality. The other thing which I need is the following lemma. If you take a summation over any interval of length q by 2, summation over interval of this is equal to less than or equal to A plus Q log Q. Let me prove that. Where alpha is approximately A over H. Have you seen this theorem? How many of you have seen this result? Okay, therefore since this thing is a little tricky, therefore I will do first the special case, see what is going on in the special case, and then we will do the general case. Okay? Therefore, let us assume alpha equal to A over Q. Okay? Once we assume alpha equal to A over Q, I want to know how this alpha H will look like. Okay? Therefore, this is 17 over 23 times H. And if this H runs only over an interval of length Q by 2, therefore this funny number will probably look like A over 23 for some A. Correct? I take the 17 over 23, multiply by H and look at the nearest integer. When you look at the nearest integer, then it will look like A over 23. Correct? And this A can come at most twice. Once from the left hand side and once from the right hand side as the nearest integer. Therefore, once has A and once has 23 minus A. Therefore, every A can come at most twice. Good? And therefore, what is the worst? And 0 can come at most once. Because when H is 0 mod 23, H is an interval of length Q by 2, and I never claimed what the interval look like. Therefore, it can be any interval of length Q over 2. And consequently, the 0 multiple of 23 can be in that interval. If a multiple of 23 can be the interval, it will be 0. Therefore, the 0 can come at most once, and every A comes at most twice, and you write all of them, okay? And then you want to see what is the worst case. Good. What is the worst case? The worst case would be a 0, and then a 1 over 23, and another 1 over 23. I mean, I am saying worst case meaning when this funny number is very small. The claim is that this funny number cannot be very small for various values of H. That's all what I want to claim. This alpha H cannot be very small for various values of H. It can be 1 over H at most twice, 1 over 23 at most twice. It can be at most 2 over 23 at most twice. It can be 3 over 23 at most twice. And 4 over 23 at most twice. And this is really the worst case. Good? And therefore, their reciprocals will look like 23 by 1, 23 by 2, 23 by 3, 23 by 4, etc. at most twice. And that summation will be something like a 23 log 23. Good? That is the Q log Q. But on the other hand, there will be 0. And that will be a serious problem. And therefore, if that for some H this value is 0, I take this A. Because that's why I wrote that minimum of A, and therefore the A will occur at least at most once. Therefore, A will occur at most once, and this will occur Q by 1, Q by 1, Q by 2, Q by 2, Q by 3, Q by 3, etc. Is it okay? This is the same thing which I am going to do in the general case. In the general case also, what we want to do is essentially when you plot them, except for 2 of them, then each one of them will be distant apart. This will be a distance of at least 1 over 2q. This will be at least a distance of 2 over 2q. This will be at least a distance of 3 over 2q. The next one will be at least a distance of 4 over 2q. That's what would happen. If I prove that, then I am through. There is one which is closest to 0, and for that one I take the value a. For everything else, it is at least 1 over 2q, therefore 2q by 1 plus 2q by 2 plus 2q by 3, etc. Correct? Therefore, essentially, I have to prove that these numbers are not too close to each other, they are distant apart. The numbers are distant apart by an amount 1 over 2q. If we prove that those numbers are distant apart from a level 1 over 2q, then I am through. If the distance are 1 over 2q level apart, then there can be one element which is close to 0. For that I will take a, and the other element is at least 1 over 2q distance from that, and therefore from 0 it is 1 over 2q distance. The other is at least 1 over 2q distance, and therefore this is 1 over 2 over 2q distance, 3 over 2q distance. Is that clear? Okay, and now let's do that. If you take a h1 and a h2, then you are looking at alpha a over q, h1 minus h2 plus beta into h1 minus h2. That is your alpha h1 minus alpha h2. Alpha h1 minus alpha h2 is large is what we have to prove. Since alpha h1 minus alpha h2 is large, you have to prove. And this number is non-zero because h1 is not equal to h2, because they are in the interval of length q over 2, and therefore this number is at least 1 over q minus beta is at most 1 over q square. h1 minus h2 is at most q over 2. Since h1 minus h2 is at most q over 2 and beta is at most 1 over h square, therefore this is 1 minus 2q. And therefore this is scalar 1 minus 2q. Okay? Therefore these fractions are distant apart. You see, that's all exactly what we, even when I took alpha equal to 17 over 23, I did not use the fact that it is rational. I only used the fact that these fractions are distant apart by a level 1 over 23. And therefore, as long as that is there, then we are through. And that is there, because you are only allowing h to run over into q over 2, and therefore it is at least 1 over 2q, and that is true. Next. Oh God, there's no next, no time. I will continue. Yes, sir.
What is the right constant there?
Oh, exact constant. Probably I don't know. Maybe you can take 5 or 6 or something like that. But if you are really interested in exact constant, these are the type of problems which Helfgott needed for his ternary Goldbach problem, where of course the exact constant is very important for him because he was really trying to prove that the major arc is less than the minor arc, and that gives you a slightly complicated argument of this type to give you the best constant that one can probably get.
Should be less than q by 2, that's for sure. So I was just curious.
What is that?
That constant should be less than a by q by 2.
Q by 2.
Q by 2, yeah.
The constant has to be constant, it's not Q. Okay? Good. I think that's the time for me, I think. No.
A is the constant. A is the any constant.
A is any fixed constant. You know, see, the whole point is that you can sum up only these funny things. You can never sum up this funny thing. You can never sum up this funny thing essentially because theoretically alpha h can be very close to 0. Once theoretically alpha h is very close to 0, that already would really dominate. And therefore you need some saving feature. And you will always have a saving feature in whatever you are doing. For example, in Wales estimate.
Okay, I guess we have time for a couple of questions and comments, if you have any.
Yes.
Sir, I was curious when you said small vision, minor arc has a small vision. Is it zero measure or what?
Not a zero measure, major arc.
Minor arc is like
Minor arc, no, minor arc is a bigger measure. Major arc. You see, because what is that? You see, it is, okay, it is a union of small arcs, okay, and each arc length is 2p over qn, correct? And then you are now taking the summation over aq equal to a1 to q, aq equal to 1, and then take a summation over q equal to less than or equal to p. When you take the a summation, this will go away. When you take the q summation, you will get a p square. And p is assumed to be n power 1 over k. Therefore, this thing is only of the measure n power 2 over k by n, which is extremely small. But that is what gives you the major contribution, because that is where the peaks are attained. Otherwise, it is uniformly small. Yeah, something else? Why is it peak obtained like that? Okay, that I will explain in a minute. Okay, oh, I don't have time, but okay, can I take 5 minutes more? Because I need it. Okay, what is your f alpha? F alpha, okay, I am taking f of a by q. F of a by q is e a by q m power k m less than or equal to p. That's what I am looking. No, this is my f alpha. Now I can do the following. I collect those m's which are r modulo k, and then sum it over all possible r. Okay, I take the r modulo k and sum it over r. Then if m is r mod k, then this is e of a by q r power k. And this e of a by q r power k comes outside the summation. Therefore, what you have is a summation r is equal to 1 to k, 1 to r equal to 1 to q, e of a by q r power k, and this is essentially m over q. M equal to rq and m less than or equal to p is essentially p over q with an error term which is O of 1. Correct? And this number is what I called SQA. And therefore, this is practically p times SQA by A. Yes. This is more or less the first proposition, that this f alpha is something like a p times SQ by q. Okay? And this SQA one can prove to be less than or equal to q power 1 minus 1 over k. But even though we would even expect probably some sort of a square cancellation should happen, etc. And therefore, essentially, see, if this is of a smaller order than q, something like a q power minus 1 over k, then you see that this number is inversely proportional to q, but not too small. Okay, and it will be something like a small, still a positive power of q, because this is still a negative power of q, because this will be something like a q power minus 1 over k. Therefore, that's what happens, and that is actually much more clearer. The original problem of the partition That is essentially because then when you wanted to evaluate it A over Q, you essentially throw the point to infinity because there is a modular transformation, and therefore you know exactly the value of A over Q, and that would clearly show that the smaller Q gives you a bigger denominator, bigger contribution. Because in the partition function, there is something called a modular transformation, which would essentially say that the value at any A over Q is related to the value at infinity, I infinity, and the value at I infinity can be easily evaluated. Therefore, the value at A over Q can be evaluated, and that would give you that. And that is essentially what people tried. Okay, whatever that worked for the partition function by Hardy and Ramanujan should essentially.
Okay, so that we can have a little break, let's thank Professor Balu once again.